Hi everyone, welcome to the fourth lecture of data mining and machine learning, and this will be the second part of our classification module. And let's look where we are in our course. So we are still in week 2, so second lecture in week 2 dedicated to classification. And last week we discussed some basic assumption about the classification problem so that we have a true distribution which generates our data in an IID fashion, independently and identically distributed. We discussed concepts like the true error and base optimal classifiers, and we discussed train validation test splits and evaluation on these different data sets, train validation test sets. We had the confusion matrix. And the main topic was were three classifiers: k-nearest neighbors, naive Bayes, and decision trees. And we'll continue today with with two more classifiers, namely random forests and support vector machines. And they are some of the most powerful classifiers out of the machine learning toolbox. So we'll discuss them in more detail, but let me just give you a high level intuition about random forest first, like illustrated with a drawing from my 5-year-old. So last week we had a decision tree, so we had one data set and we trained a decision tree. So a decision tree yields a nicely interpretable model, but often the performance is not top. And so it either overfits to the data or we just don't get like really the correct decision tree out of it. And the idea of random forest is really to, well, if one tree is not performing well, maybe many trees or a forest is performing well. So rather than training a single decision tree on a single data set, we train now many decision trees on many different data sets, essentially. And you see that all these trees, they are pretty diverse, and so like they essentially represent some diversity. And in the end, we will classify by aggregating essentially their predictions, so by either majority vote or we average the yielding classifiers. And the main point is now, how do we train multiple decision trees when we have only one data set? And the idea will be essentially that we generate artificial data sets by essentially resampling our original data set with replacement. And doing this is called is a so-called bootstrap. So resampling your data set with replacement is a bootstrap. So you essentially bring in some randomness in these artificial data sets, and each of these decision trees is trained now on one of these bootstraps. So therefore we will have a diverse set of trees, and moreover we will slightly randomize also this card learning algorithm, so our decision tree learning algorithm. And this will yield a diverse collection of trees and so-called ensemble method, and by aggregating these classifiers we will get random forests, and these are some of the strongest classifiers to date. And to illustrate the other topic for today, support vector machines, let's do a short excursion into my kitchen. To illustrate the point of support vector machines, here I'm in my kitchen, so what better way is there to explain classification algorithms than with fruit? So this was for decision trees, and oh yeah, so here we already have a very nice classification problem. So we wish to classify chilies against cucumbers. And it seems that it's not too tough classification problem. So everything here is chili, everything here seems to be cucumber. So we could have like a separating hyperplane here. And now in order to represent this hyperplane, I will just take some random book from my bookshelf. And so for example, I could just squeeze this in here. Yeah. So this does a good job. So everything up here is on the left hand side is chili. Everything on the right side is cucumber. But somehow I'm not perfectly happy. So since you see there's a bit of slack, so there's quite some distance between the training examples and this hyperplane. And essentially we can actually move this hyperplane, and it's not really clear how to position the hyperplane in here. So let's take a thicker book. So let's find the thickest book, which can just be squeezed in here. So, oh no. So this book is too thick, so I cannot really squeeze it in here without smashing the cucumbers and the chilies. So let's take a third random book from my bookshelf, and it seems that this will just work right. Yeah, so this perfectly squeezes in between the training examples. So essentially it seems that it's even held by these training examples, so supported by the training examples, and this is therefore the name support vector machine. So a support vector machine is essentially the thickest book or the thickest board or the broadest road, which can be just squeezed in between our training examples, so between positive and negative class. The second aspect we will discuss in support vector machines is the so-called kernel trick, and this has to do with nonlinear feature transformations. So figure that this is now a one-dimensional classification problem, so like we don't have 2D, so like all the training examples lie on a line, and you see now actually we cannot really work with support vector machines here, or with separating hyperplanes, so no matter where we position this hyperplane, we won't do a good job. But the basic idea in machine learning is that, so if your input dimensionality is maybe low and your data is not presented in a suitable form for your classification algorithm, what you can try is to apply some nonlinear feature transform. So with this 1D problem, and maybe we can come up with a nonlinear feature transform which actually would just map this point here and this point here, maybe this point here and this point here, and like would map this here and map this here, map this here, and map this here. So essentially we went from 1D to 2D with some warping function or with some feature transformation. And all of a sudden, by transforming our original space in a suitable way, we see that all of a sudden we can work with a separating hyperplane, like a support vector machine. And the main point is that you can always do this in machine learning. And so you can always try this to first warp your input space to a high dimensional space, which simplifies your problem. But if you do this exhaustively, then this will also be costly, since you have to do these transformations. And if you have a really high dimensional feature space, this will be expensive. And the kernel trick will be a way to do this implicitly and therefore efficiently. So here's our plan for today. So for 4 sections, we'll start with random forests. This will actually not take too long. And the main part for today will be our discussion about support vector machines. And support vector machines are a pretty involved and deep topic, and also interesting from a mathematical perspective. So we'll take it slow and do this in 3 sections. First discuss the principle, then learning as optimization problem, and then a section about the kernel trick. And this will be a rather lengthy section and actually split into 2 parts.